All right. Good evening. So this is chapter 16, part 3. And we're just going to finish out our study of probability models. Now, in chapter 16, we discussed the geometric probability model and the binomial probability model. And for part 3, we're going to take a look at how we could use the normal model to approximate the binomial. Now, in this first bullet point, when we read this, it says, when dealing with a large number of trials in a binomial situation, making direct calculations of probabilities becomes tedious or outright impossible. So if you recall from yesterday's notes, okay, the binomial probability model is basically with this formula, probability of x equals ncx times p raised to the x times q raised to the n minus x. Now, the problem comes in really with this calculation. So if we're forced to do this by hand, this combination becomes really tedious, really hard. And in addition, we might be able to use binomial tables to calculate this, but if n is really too large, our tables don't go that high and it just becomes problematic. So there becomes a shortcut, and we're able to use the normal model to approximate the binomial probability. So there's a couple key words there. First off, we are going to only approximate. The normal model gives us a pretty close approximation. Not a great approximation, but a pretty close approximation to what the binomial is going to give us. Okay? The reason we do that is twofold. One, it's pretty easy, because on a calculator, we know how to use the normal CDF function. This is way back in part 1. And it's also easier because there's one table. And that's in the back of the book, or that's in your table of formulas or tables that's given to you in the AP exam. So we would really love to be able to use the normal model. And it makes our calculations a little bit easier. But the key is it's not perfect. It's only an approximation. Okay. The other issue comes in the fact that the binomial model is used to describe discrete variables. Remember, these things are ones that we count, whereas the normal model is a model that's used to represent a continuous variable. So there's another issue. Okay, so it's different types of variables, so we're going to have some problems when we do this. Now, in order to do this approximation, so binomial model is approximately normal if we can expect at least 10 successes and 10 failures. So for this condition, we do a simple calculation. We do n times p, so the number of trials times the probability of success, and we check to make sure it's at least 10, and then we check n times q, so number of trials times the probability of failure, and we make sure it's at least 10. Okay, so there's a quick note. When we use the normal model to approximate the binomial, we are using a continuous random variable to approximate a discrete random variable, okay? So this is our first hiccup, okay? And one reason, it's an approximation. It's close, but not really great, okay? So when we use the normal model, we're not going to calculate the probability that a random variable will equal a particular value. So if I want the probability that x equals, let's say 2, for example, I need to use the binomial PDF to calculate that, okay? If I'm calculating the binomial, the probability that x is less than or equal to 2, I can use the binomial CDF and calculate that, or I can approximate that by using the normal CDF. And that's what today's lesson's about. Okay, and lastly, some AP tips. So remember, and I said this earlier, the AP rubrics usually have 3 requirements for probability problems. You must name the distribution. So right now, just a quick review, we have 3 distributions we've talked about. We've talked about the geometric, we talked about the binomial, and we also have the normal. So you need to state which one you're using. You need to identify the correct parameters. Remember, the geometric, you need a probability of success. The binomial, you need n and p. And the normal, you need mu and sigma. and you need to find the correct answer. So we are doing a checklist when we grade the AP exam. Did you mention all three of those things? And then remember, calculator notation does not earn points. Okay? We don't take off points, but we don't give points for calculator notation. So always write out words and notations as I've been doing in the problems. Now the name, you can write out the name in words. You can use the formula. The formula will give you the points for the name, or you can write both of them, okay? And then remember, parameters, you should use standard notations, and those are the ones I've been giving you. All right, so let's try example 1. So the archer in the previous day's example will be shooting 200 arrows in today's lesson. So if you recall, the probability that the archer makes a bullseye is 80%. Now for today, the archer is going to be shooting 200. Now remember, this is a binomial situation. So there's a success failure. You either make the bullseye or you don't, okay? Probability of success is fixed at 80%. Shooting is independent of one arrow for another arrow. And then it's a binomial because it's a fixed number of trials. There's 200 arrows that we're shooting. So part A, what's the mean and standard deviation of the number of bullseyes that she might get? All right, so if you recall, the formula for the binomial, the mean is equal to n times p. So that equals 200 times 0.80. And then I did that earlier, and I got 160. And that should be bullseyes as the units. Okay. And then our standard deviation, sigma, equals the square root of npq. So that's going to equal the square root of 200 times 0.80 times 0.20. And that is going to equal 5.66. And again, the unit there is going to be bullseyes. Okay. All right, part B. Would a normal model be appropriate to use here? Okay, so we check our conditions. The first calculation is n times p. So n is 200, p is 0.80, and that equals 160. So that is greater than or equal to 10. We check n times q, which is 200 times 0.20, and that is equal to 40, and that is equal to greater than or equal to 10. Since both of those conditions are true, yes, the normal model is appropriate. All right, so as normal model is appropriate, I can now use the 68, 95, 99.7 rule to describe the distribution. All right, so if you recall, for 68%, I'm going to add and subtract 1 unit of standard deviation. So I'm going to start off by taking my mean, and I'm going to have 160, and I'm going to subtract 5.66. And then that's going to give me my lower boundary. So let me put a comma instead of a minus sign here. And then for my upper boundary, it's going to be 160 plus 5.66. So I get 154.34 to 165.66. All right, for 95%, I'm going to do pretty much the same thing, but this time I'm going to subtract 2 units of my standard deviation. And then I'm going to add 2 units of my standard deviation. So those boundaries are going to be 148.68 to 171.32. And then for 99.7%, I'm going to take 160 plus 3 units of my standard deviation. And then I'm going to take 160 minus 3 units for my standard deviation. And then I get the interval 143.02 to 176.98. And D, would I be surprised if she only made 140 bullseyes? Well, look at that. Yes, I would be, because it's more, or yeah, 3 standard deviations below the mean. Okay, matter of fact, the probability this happens is less than 0.0015. Now that was found by taking 1 minus 0.997 because it's outside the 3 standard deviations and dividing it by 2 because it was to the left, okay, according to the 68, 95, 99.7. Okay. Example 2. So based on concerns raised by his preliminary research, the biology in that example we've been dealing with for frogs decides to collect and examine 150 frogs. So N is 150. Assuming that the frequency of the trait is still 1 out of 8, so the probability is still 1 out of 8, determine the mean and standard deviation of the number of frogs of the trait that you should expect to find in this sample. So again, the mean is going to be N times P, which is going to be 150 times 1/8, and that's where we get 18.75. And then my standard deviation is the square root of NPQ, which is going to equal the square root of 150 times 1/8 times 7/8. And that's going to give me 4.05. All right, let's verify we can use a normal model to approximate the distribution of the number of frogs with that trait. So first, let's check N times P, which is 150 times 1/8, which is going to be 18.75. That's greater than or equal to 10. And then let's check NQ. So that's going to be 150 times 7/8, which is going to equal 131.25, greater than or equal to 10. So yes, I can. All right, so C. So he found the trait in 22 of his frogs. Do we think that proves his trait's unusual or is more common? All right, so let's find the Z-score for 22 just to verify that. So 22 minus 18.75, that's the mean, divided by the standard deviation, which is 4.05. And when I do that, I get 0.8. Okay, so no, 22 is only 0.8 standard deviations above the mean. Okay, it's not unlikely that this could happen as a result of natural sampling variability. Okay. All right, example 3. So an airline, believing that 5% of passengers fail to show up for flights, overbooks or sells more tickets than there are seats. So suppose a plane will hold 265 passengers and the airline sells 275 tickets. What's the probability that the airline will not have enough seats? So someone will get bumped. All right, so this is a binomial situation. Okay, I've checked all of the conditions. So a couple of things we kind of have to figure out. The first is our probability of success. In this case, we're going to see what's the probability people show up. So that's the opposite of this, and that's going to be 0.95. And the number of trials. In this case, the trials are the number of tickets sold, 275. Okay. What we're trying to figure out is the probability that we get more passengers than we have for seats. So we want to find the probability that X is greater than or equal to 266, because that means we're oversold. 265 is fine. All right, so I'm going to use the calculator. So I'm going to do 1 minus the probability that X is less than or equal to 265, because remember the calculator only thinks less than or equal to when I use the binomial CDF. So let's go to the calculator. 1 minus second vars. I'm going to go all the way to binomial CDF. My number of trials is going to be 275. My probability of success is going to be 0.95. And I want to find less than 265. And I hit paste, and I hit enter, and I get this probability is equal to 0.116. All right, and that was the binomial. Now let's take a look and let's see, what if I approximated this using the normal? By the way, could I use the normal? Yep, so n times p is going to equal 275 times 0.95. So let's check that real quick. 275 times 0.95. And I get 261.25. And then NQ is going to be 275 times 0.05. And that's going to give me 13.75. So both of these are greater than or equal to 10, so I can use a normal approximation. So we want to find what's the probability that we get more than 266. So if I'm using a normal probability, I would do normal CDF of 266, comma E99, comma the mean, which we found was n times p. So mu equals n times p, which equals 275 times 0.95, which equals 261.25. And our standard deviation, which is the square root of 275 times 0.95 times 0.05. So let's do that one. Square root of 275 times 0.95 times 0.05. And I get a standard deviation of about 3.61. Okay, so let's see what that normal CDF would give us. So second distribution, normal CDF. My lower boundary is 266. My upper boundary is E99. My mean is going to be 261.25. And my standard deviation is 3.61. All right, and I get 0.094. So, as you can see, you get pretty close to the probabilities, but not exact. Okay, this is why this is called the normal approximation to the binomial. Okay, all right, how about example 4? So, shortly after the introduction of the euro coin in Belgium, newspapers around the world published articles claiming that the coin was biased. The stories were based on reports that someone had spun the coin 250 times and gotten 140 heads. That's 56%. Do you think this is evidence of the euro being unfair? So the question is this unusual? This number is unusual. So let's check it. If everything was fair, let's see what we would expect to get. So n is 250. If this was a fair coin, it would be 50%. So my expectation is my mean, n times p, and that is where I get 125. My standard deviation is going to be the square root of 250 times 0.5 times 0.5, and that is where I get 7.9. Let me do that one. All right, square root 250 times 0.5 times 0.5. And I get 7.91. Okay. So let's see how unusual 140 is. So z equals 140 minus 125 divided by 7.91. So 140 minus 125 divided by 7.91. And I get 9. Okay. So we get within 2 standard deviations. Do I think this is unfair? No. No. 140 heads is within 2 standard deviations of the mean. And there are other ways you could justify your answer on that. All right, last question. So vitamin D is essential for strong, healthy bones. Our bodies produce vitamin D naturally when sunlight falls upon the skin, or it can be taken as a dietary supplement. Although the bone disease rickets was largely eliminated in England during the 1950s, some people there are concerned that this generation of children is at increased risk because they are more likely to watch TV and play computer games than spend time outdoors. Recent research indicated that about 20% of British children are deficient in vitamin D. Suppose doctors test a group of elementary school children. All right, so from this entire paragraph, I get the probability someone has vitamin deficiency is 0.20. So part A, what's the probability that the first vitamin D deficient child is the 8th? Well, first is on the 8th. This is a geometric situation, right? We want the probability that that first success happens on the 8th. So that means I want failure 7 times before, and then I want success on the 8th case. All right, and when I plug that into the calculator, I get 0.042. Okay, B, what's the probability that the first 10 children tested are all okay? So there's a couple ways you could do this one, right? But probability of not having vitamin deficiency in this case is 0.80. And we want the first 10 children to be okay. So this would be 0.80 to the 10th power, which would equal 0.107. Okay, C. How many kids do they expect to test before they find one who has vitamin deficiency? Okay, expect is a mean. Now, which mean do I want to find? So we want to do this before finding one. So this is before finding a success. So that means I want the geometric mean, 1 over p. So this is 1 over 0.2, which is going to give me 5. All right, D. So they will test 50 students at the 3rd grade level. So 50, now we have a finite set, n equals 50. Find the mean and standard deviation of number of people who will be tested for vitamin D, or who will have the vitamin D deficiency. So the mean will be n times p. So 50 times 0.2 equals 10. And my standard deviation is the square root of npq, which equals the square root of 50 times 0.2 times 0.8, which equals 2.83. Done. And last but not least, so if they test 320 children at this school, so now our n becomes 320, what's the probability that no more than 50 of them have vitamin deficiency? So we're going to do this in 2 methods, okay? So method 1, let's look at the binomial, okay? So we want no more than 50, so we want the probability that x is less than or equal to 50. Okay, so on the calculator, this is simply going to be the binomial CDF of n, 320, probability of having it is 0.20, and we want less than or equal to 50. All right, second distribution, let's find the binomial CDF. N is 320, probability of having vitamin deficiency is 0.2, my x value is 50, I hit paste. And I get a probability of 0.027. And there's your answer, done. Now let's take a look at the normal approximation. So step 1, we need to find a mean, which is going to be n times p. So we want 320 times 0.2. 320 times 0.2, and we get 64. Then we want a standard deviation, square root of NPQ, which is the square root of 320 times 0.2 times 0.8, which equals square root of 320 times 0.2 times 0.8, which equals, let's say 7.16. Okay. So we want the probability that x is less than or equal to 50. This is going to equal the normal CDF of negative E99 to 50, comma 64, comma 7.16. And let's see what we get there. Second distribution, normal CDF, negative E99, upper is going to be 50, my mean is 64, and my standard deviation is 7.16, and my normal approximation is 0.025. So look how close this was to my binomial, 0.025. So fairly close. Exact approximation. Okay. All right, and there's your notes for tonight. I hope that helped your homework this weekend.